Hello chemists and welcome to this 2-Minute Tuesday here on Bale's Chemistry. In this episode we're going to be looking at the functional group alkenes. Just a little thank you to everyone who subscribed to the channel. We keep growing and it's keep inspiring me to make even more videos. Okay, so alkenes are a type of functional group and they're seen as hydrocarbons containing at least one carbon-carbon double bond. It is of course possible to see other functional groups attached to the chain as well, but in this episode we're focused just on the double bond. All alkenes then have a general formula of CnH2n, and this can be particularly useful for quickly identifying an alkene from its formula. Alkenes are present in small quantities in crude oil, but most of them are formed after the crude oil has been separated into fractions, and then the longer chains are broken down using a process called cracking. Thermal cracking with its higher temperatures and high pressures favours a higher yield of alkenes compared to catalytic cracking. When it comes to naming alkenes, we use the usual prefix for naming carbon chains. However, we can ignore meth because it only has one carbon, so it can't form a double bond. That leads us to the suffix, the bit at the end, and it's ene or ene. Now, for symmetrical alkenes like ethene and propene, this is as far as we need to go. But when we get to butene, which is asymmetrical, we need to state where the double bond is present. We do this by placing a number of the carbon that the double bond is attached to in the name, such as but1ene and but2ene. These are known as positional isomers. Alkenes undergo electrophilic addition, which breaks the double bond and adds atoms to the molecule. Starting with the alkene, the electron-rich double bond attacks the polarised electrophile. Before in the second step, the newly created nucleophile attacks the carbocation. Remember, if you have an asymmetric alkene, then you'll have a major and minor product. This is governed by Markovnikov's rule. The major product will be the one with the more stable carbocation in step 2. There are some common alkene reactions. Forming halogenoalkanes by reaction with a halogen halide, forming alcohols via reaction with phosphoric acid, or by reaction with water in the presence of a sulfuric acid catalyst. This one goes via the alkyl hydrogen sulfate group, and of course using alkenes to make polymers. Alkenes can be formed by carrying out elimination reactions of halogenoalkanes. This involves the removal of hydrogen by a strong base such as potassium hydroxide or sodium hydroxide, which in turn reforms the double bond and kicks out the halogen. This needs to be done using a strong base with the reaction happening in ethanol, not water, and will require the harsh conditions of reflux. We can also dehydrate alcohols. A common method is to use a sulfuric acid catalyst to remove the water. But we can also use aluminium oxide in a process similar to cracking, or a phosphoric acid catalyst which is similar to the sulfuric acid method shown. Alkenes are examples of geometric isomers. We have E-ethene and Z-ethene. These form because there's no rotation around the double bond, so the groups stay fixed in their positions. The E isomer has the higher priority groups on the opposite sides, while the Z isomer has the higher priority groups on the same side. These priority groups are decided using the Cahn-Ingold-Prelog rules. And finally, we have testing for alkenes. We use bromine water here, which is orange, and it reacts with the double bond of the alkene to form a halogenoalkane, and in turn it forms a colourless solution. That's a lot of information about alkenes. Let me know if you think I've missed anything in the comments below. It wasn't really a 2-Minute Tuesday, but click here to find more of them and click down here to subscribe.